thank you for the opportunity to give a talk on the ecological impact of high-performance computing. And I will start it by sharing my slides, which is here. So the ecological impact of high-performance computing is something that got me concerned several years ago, actually already for a while. If you look at astronomers, like I am an astronomer, then the total impact of computing is not so great. It's about 6% of the total carbon budget that we produce. The majority of the energy used by astronomers is by commuting, the buildings, but also the flying to and from telescopes and the existence of telescope facilities on high mountaintops. Computing, still 6%, is divided by actually only a few astronomers. So even though the total budget is not so great, the budget per astronomer that is using computers is rather high. And then I have to say that this computing is only the supercomputing. It's not sort of the local workstations or laptops that everybody is using, because those energy is generally taken into the budget of the buildings itself. On this picture, what you see is a former postdoc and grad student, Jeroen Beedorf, together with me, working on one of our green computers. This machine is called LGM, Little Green Machine 2. It's a second version where we use high-power GPUs in order to do the calculations. And it was at that time one of the greenest machines on the planet. My name is Portegies Zwart. I'm a staff astronomer at Leiden Observatory. Now, if you look at the top 500 and the green 500, the top 500 depicts the fastest computers on the planet. I have here the top three listed: Frontier, Fukaku, and Lumi. You see they produce about 50 petaflop per kilowatt. But if you look at the green 500, Henry, Frontier, and Adastra, the top three of those, they also produce about 50 petaflop per kilowatt. And you see that all on the right, you see that all the green 500 computers are on the top 500, and all the top 500 computers are also in the green 500 somewhere. And that's so the whole business of having green computers or just high performance computing, it's sort of the same mixed bag. And that is because the total energy you produce per electricity, it's an expensive commodity, the electricity. So everybody always tries to get as many flops as possible out of a kilowatt of power. Now, I have to say that 32 European machines are in the top 500 and 50 in the green 500. So that is a good thing. It also shows that there's not a complete overlap between the two. But a few years ago, when I gave a similar presentation and looked at the similar data, it turned out that actually the Europeans had a minority in the green 500, and they were more energy unfriendly in computing. So we are going in the right direction, but on general, the green 500 is not necessarily the way we should go. It's not necessarily that we should be more advanced in how to use a computer and how to power the computer, because an important part in running the computer is not necessarily how you use the power, but also what's the origin of the power and what you do with the excess heat. That is excellently done in the Lumi supercomputer, which is the finished machine. It uses 100% hydroelectric power. The hydro plant is nearby, and the excess heat of the computer is actually used to heat the local townhouses. So in total, in a year production of Lumi, 12,400 kilograms of CO2 are being reduced, because those houses do not need to burn oil or anything non-renewable in order to heat their houses. So this computer actually is ecologically negative in terms of how much CO2 it produces. And I think it should be an example of how we can and should probably build supercomputers in the future in order to prevent the pollution of our only one and only planet. Now, everything in computing has to do with Dennard scaling and Moore's law. The Dennard scaling, the Moore's law, you all know, the doubling of the computer time every 2 years or so, 18 months. And you see that here in the orange points. Basically, the number of transistors per surface area continuously from the 70s up to today. But as you see also is that there is a breaking point at around 2005, where the total number of single-threaded performance stopped increasing, the frequency of computer clocks stopped increasing, and the total power per watt also stopped increasing. This is compensated by, in order to keep Moore's law going, this is compensated by the number of logical cores per surface area, or the total number of logical cores actually. So the total computing power, the high performance we get today, and the continuation of Moore's law is a consequence of the scaling in which we build computers. Computers get bigger and they don't get faster as such. And that also means that if they get bigger, they also start producing more and more energy. Now you can also see that in this figure where I put in the time to solution, which is actually the thing that matters. That's the thing we have to wait. How long do you have to wait to get your solution as a function of the CO2 production? And I use it as CO2 production rather than, for example, the number of kilowatts, assuming that all the machines and all the instruments I have here are powered by sort of a European mix of energy, or maybe a Dutch mix of energy. Now what you see on the red diagonal line is the line that goes through a PhD in astronomy, or an average PhD maybe, and it sort of scales with the performance, the high performance applications that people tend to run: population synthesis, stellar evolution, gravitational dynamics, cosmology. They all follow sort of this line. And if you're simply more patient, you have larger calculations, you have to wait longer, but you also produce more CO2, or you use more energy. If you compare that to an average astronomer, this is a bit above the line. That is because the professional astronomers travel a bit more than the average PhD student, and they also use bigger computers, and they commute, I guess, with car, while the PhD students use a bicycle. And also you see the ALMA observatory, which actually is a little bit low here because I didn't take into account here the energy plant, which is an oil burning generator near ALMA in order to power the machine. They're working now on solar panels in order to improve this, but the ALMA point still should be 2 orders of magnitude above the current point. It's comparable to the LIGO emission and the gravitational wave research. And what you see in the purple line is the use of a supercomputer. If you share the computer optimally and use one core, you have to wait very long to get your answer, but you do not produce so much CO2 because you share it with all the other people, but you also use the computer. But if you start using more cores, your relative proportion of using your wall clock time reduces, but also the amount of CO2 you produce goes up. And if you use an entire machine of, let's say, 1 million cores, the total CO2 production of your calculation becomes comparable to launching a rocket into space. Now, the use of a computer, of course, only you have chips which have many cores, and what I depict here is what we call the Z-plot, which is the performance as a function of the energy to solution. So if you, of course, we all want high performance computing, we want a faster computer, but we also want to be energy friendly. So is there an optimum in the performance and the energy friendliness of your calculation? And yes, there is. And that is what you see here. If you use one core of a 192 core virtual cores machine, then you see that using one core actually is rather inefficient because the rest of the machine is idle and it still powers the monitor or the hard drives, etc. And the machine has to be hot. But if you overclock your one core, which is depicted in the blue and the red points, using 3 gigahertz and 4 gigahertz rather than the 2.2 gigahertz in the factory settings, you see that your performance indeed goes up, but your energy to solution actually disproportionately increases. So the message here is don't use overclocking cores, but use just the factory settings for your computer. We have played this game, and to my shame, but it's better to use just the standard settings. Now, if instead of one core you use 2 cores or 4 cores or 8 cores or 64 cores, you see that the performance goes up, so the time to solution goes down, but also the energy to solution goes down. And it is simply because your computer is more efficiently using the energy and it becomes faster in order to get to your solution. And you see that the optimum actually is where you have the maximum number of logical cores. If you go beyond the logical cores into the virtual cores, your performance still goes up, but at the cost of extra energy production. So the message here is don't overclock your workstation and use it for the logical cores, and don't use the virtual cores for your calculation if you want to be energy efficient with your calculations. Of course, if you want a faster solution, you have to pay for it in terms of polluting the earth. Now, another aspect of energy efficiency and high-performance computing is the language you use. So you have something like runtime performance, and then you look at as a function of the programmer productivity, because another aspect of high-performance computer is how much time do you want to spend in order to optimize or work on your code. And if you look at runtime performance, assembler, of course, and machine code have the highest performance which you can get. It's easiest to, well, it's hard to optimize, but you can optimize it better than anything else. But it is at the cost of programmer productivity. It is very expensive in terms of human time. And that is also an aspect that you have to take into account. If you go to Fortran, C, C++, they sort of enter the middle range. They're relatively easy to program. They are relatively productive, but the performance goes down with respect to assembly. And of course, you can program assembly in such a way that is almost as fast as C++ and the other way around. But that is the programmer efficiency you have to put in. Now, on the top bar here, you see Python completely to the left, low performance, but high productivity. It's relatively easy to program Python, but it is relatively hard to get a good performance out of it. And Rust, which have a high runtime performance, and it is a high productivity. Rust and Haskell would be, and Julia would be, in my perspective, the languages of choice to teach to students, because they're fast, they're efficient, they're easy to program, and they're easy to program efficiently, where Python is, yeah, it's easy to program, but it is hard to make it very efficient. And assembler, basically nobody really wants to do it except if you really must. You can also look at the efficiency, what it means for you in the end of the day. So that's the time to solution as a function of, in this case, CO2 production. And then I have to say that this graph was made with a slightly off measure for the CO2 production per flop. But in the end, it doesn't, it's just a scaling relation. You see that Python it takes a long time to run. And this is sort of the standard Python I see my colleagues in astronomy programming in. And as a result, it produces a lot of CO2. And this red dotted curve is tuned up the C++ performance in time to solution as well as C production. And you see that even per flop, Python produces more CO2 and it is slower in the machine itself, the operations, than, for example, C++ or Fortran. Of course, Python you can optimize by using Numba or using a YIT compiler or using NumPy efficiently. Or embedding maybe assembler code. And that is something that on the bottom right inset is being done by a bunch of people who indicated that Python can be as efficient as C++ or Fortran, as long as you program it efficiently and in the right way. Now, what makes a computer green in the end? Of course, you want your computer to be using renewable sources, as it's done with Lumi, or if it's done with many supercomputers in Europe these days, but also by using the excess heat produced by the computer and use that in order to heat, for example, swimming pool or a tropical swimming paradise, or maybe houses of people or office buildings. Then you can even achieve a negative CO2 production per flop, which would be very desirable. Using GPUs, ARM processors, FPGAs, or other many core architectures, of course, helps. It is the single CPU processor which really is relatively energy inefficient. The GPUs are amazingly more energy efficient than the normal CPUs. Use multiple cores, parallelize your code by all means. It makes the wall clock time go down. It also makes the ecological impact of your calculation go down. It makes it more efficient, but you have to pay for it in terms of human time. You have to spend time in order to parallelize your code. But apart from the fact that it is fun to try to optimize your code and parallelize it as efficiently as possible. Running at low clock frequencies is generally better than running at high clock frequencies, although there is an optimum there. And the optimum is probably around the factory setting at which you buy your computer, or if you use a supercomputer on which the supercomputer is being set. And use an efficient language. And here it says certainly not Python. Well, certainly not Python. Not Python as sort of the vanilla type Python as it comes out of the package. But if you use sort of a YIT compiler or NumPy efficiently, or you embed C++ code, then of course Python would be a fine language to use. Now I would like to finish with a few conclusions. We spent enormous resources on energy and CO2 production for scientific computing. And I think at some point we have to realize what we are doing. And one way by starting this discussion is by, if you do a large number of calculations and you write a scientific paper about it, mention in your paper how much energy is being produced in order to do your calculations. I think it would be good to be aware of the fact that we are using energy also for doing our science, and at some point somebody will knock on our door and say, hey, it's very nice that you do this very nice research, but how much energy did it cost us, and what is the ecological imprint of your calculation? If you would run at normal or low clock frequency, parallelize your code, ideally on the GPU, optimize your code, use the optimized compilers, use always with the optimized setting, although don't overdo it in order to, it may cost your science in the end. And you can save a big factor in your CO2 production. And that's all. Thank you very much.